Want to discover a new efficient way to encode and decode DNA data? In this video, we'll dive into the DNA coding exercise, and I'll show you how to convert a DNA char list into a bit string and convert it back using tail call optimized code in Elixir.
All right, today we're tackling the DNA encoding exercise in Elixir.
Howdy, I'm Kevin, and in these videos, I explore AI tools to help us learn. For example, I use NotebookLM to explain concepts and Copilot to autocomplete code and automate processes for efficiency. I balance AI with my experience as a senior dev to show you how to solve the exercises and keep AI honest. Watch this video for a comprehensive presentation of the exercise and the Elixir concepts, and of course for my solution.
This is where we're going to introduce the accumulator pattern. And honestly, this is Elixir's secret weapon for writing scalable, efficient code that just feels right.
So what even is tail call recursion? Well, the official definition is pretty straightforward. A function is tail recursive if the absolute last thing it does is call itself. That's it. And that one simple rule has massive implications for performance. Because the Elixir compiler can optimize it, completely avoiding a growing call stack. It basically turns the whole thing into a super efficient loop behind the scenes. Now, how do we make that happen? The key is the accumulator. Just think of it like a variable we pass along that holds the result of our work so far. It carries the state from one function call to the very next, building things up piece by piece until we finally hit our stopping point and return the finished product.
I have downloaded the DNA encoding exercise using the Exercism CLI and loaded it into VS Code. I've also run my generate docs prompt, which brings information from the README and hints file into the source code as function documents.
It's time to build the nucleotide to binary map. We're going to start small and use one of Elixir's most powerful features, pattern matching, to write some incredibly clean and efficient code.
The first step is to encode the individual characters, A, C, G, T, and space, into a binary format. So we will use the encode nucleotide function over here, and if we get a space, then we should return the binary 0. Well, all right. Github Copilot is kindly bringing the information in out of the README, so we'll just accept it. Let's just check. A is 1, C is 2, or the binary 1, 0. G is 100, or 4. And T is 1000, or 8. And let's see if we got that right.
Now let's do the reverse. We need to implement decode nucleotide, which takes a number like 1 and gives us back the character A. And we're going to use the exact same elegant pattern matching approach, just, flipped.
Step 2 is to reverse that process, getting an encoded value, turn it back into the character. So if we were to receive 1, then that's A. Thank you, GitHub Copilot, for finishing that for me.
Okay, with our little helper functions in place, let's move on. We're now encoding the entire DNA sequence. We're leveling up from a single character to a whole list, and we're about to build our very first tail recursive function from the ground up.
Another way to think about the stack in tail call optimization is like a single shared journal passed among coworkers instead of needing individual private memos. When each coworker finishes their task, they simply update the journal and hand it directly to the next person without needing to save their own memo on their desk. The journal is the only thing needed to complete the process, which is why the compiler can optimize away the stack. Step 3 is where things start to get interesting. We're supposed to take a char list, which is the DNA, and recursively encode that. So let's do this the old school way, and then we'll convert it to the tail call optimized version. So what we'll do first is we're going to create a private function to do the recursion. And let's say this is a build encoding. And it takes the DNA, and since this is the base case, we'll say, all right, when it gets an empty list, we return an empty bit string. And then if we receive a head, first one, the nucleotide and the rest, we could encode the nucleotide and then build the encoding on the rest. And then, of course, we need to call it. This should work. All right, but this is the old school way and doesn't use tail call optimizing and or the accumulator. So let's add that. So what we'll do here is we're going to say that we're going to start out with the empty bit string. This is our accumulator. When we get an empty list, whatever we've accumulated so far, we're going to return. Let me pause that for a second. So now we're going to get the list with the first one, the nucleotide and the rest, and the accumulator. What we want to do is update the accumulator to be whatever we had before the accumulator, plus encoding this nucleotide. Then the magic sauce in the tail call optimization is to then call the exact function with the exact signature. So we want to build the encoding with the rest of it and the accumulator.
Okay, let's jump into our final coding section, decoding the DNA sequence. We're going to apply the exact same recursive pattern, but backwards. This will really show you just how flexible and powerful this approach is for all kinds of data transformations.
Using the accumulator pattern is the idiomatic Elixir way to write memory-safe recursion. By making the recursive call the last operation, the tail call, you allow the beam to reuse the current stack frame instead of allocating a new one. Your recursive function won't cause stack overflows even when handling large inputs. Okay, decoding the char list is a lot like encoding it was. We'll need to do a recursive function to decode it. This time we're given the bit string and we want the letters back. So let's create a private function. Let's say build decoding. And when we get to an empty bit string, we want to return whatever we've accumulated so far. So that'll be do accumulator. Then, all right, let's take what GitHub gave us and take a look at it. So build the decoding, we pattern match the first nucleotide and the rest of the bit string and our accumulator. The accumulator becomes the decoded nucleotide prepended onto the accumulator. And then, in tail call optimization fashion, we call the same function again with the rest of the list and the accumulator. So let's wire that in. So this says we're going to build the decoding starting with the whole list, and we're going to start with the whole bit string and an empty char list. Now this will fail, and the reason this will fail, well, let me run the test and show you why this fails. This fails because we were expecting space ACGT, but we got TGCA space, and that's because when we were building the list, we kept piping the first thing onto the front of the list, so by the time it was all over, the first thing is the last character. So we need to reverse this. There are handy-dandy functions to do this, but the exercise is wanting us to practice with our newfound tail call optimization skills, so we'll build it. So we are going to create a function called reverse char list, which the stop situation will be when the list is empty to return the accumulator. Otherwise, we're going to pattern match the head, the tail, and the accumulator. We will update our accumulator to be the head, and then we will call the tail call. And so basically this ends up reversing the order of the string. And we want to use it right here. When we get to the bottom of our decoding, we want to reverse the entire list. So we're going to take the list we have and an empty list. That's going to reverse the orders. You may have read the recommendation to create a private function by prepending the do underscore in the hints file. You definitely should separate the public function from the private internal details, but I think the community strives for more descriptive names for your private functions. The instructions make a big deal out of tail call recursion, claiming it's more efficient in terms of processing and is much better on memory, but they don't offer any statistics as to just how much better. So what I've done is I've taken our concluded DNA exercise with the tail call optimized functions, and I've grabbed the encoding bits out of it and put it in a new module called bad DNA that does the recursion but does it the old school technique. I've then loaded up a library called Benchy. Benchy will allow you to measure the performance and compare one function versus another. So I've given it the old school encoding technique and the new code and the new tail call optimized version, and our DNA is 1,000 characters long. All right, so now that Benchy is done running, what did Benchy find? It found that, let's start here, from an instructions per second perspective, regular recursion, the old school way, is 20 times slower. And from memory perspective, the regular recursion used, let's call it 1,000 times more memory. Now, for this little exercise, is it a big deal? No. If this was your web server host farm or your back-end processing, or you had hundreds of thousands of these to do, then yes, absolutely, it makes a big deal. So tail call optimizing your functions out of habit is just the right thing to do. I'm always refining the content based on the ever-changing AI landscape. What AI content did you like? And what AI feature would you like to see me use in a future video? Let me know in the comments.
So what are the key things to remember? 1. Always use tail call recursion for enumerables to keep your memory safe. 2. The accumulator pattern is how you unlock that power. 3. Always reach for pattern matching before you think about conditional logic. And finally, use that public/private function pattern to keep your APIs nice and clean.
Like and subscribe so you don't miss the next optimization. Tail call into the playlist to recursively build your expertise one powerful function at a time. See you there.